Okay, as we all know, this is a quadratic equation and the graph of it is just a parabola. And we have a very nice formula for its vertex. It's just at x equals negative b over 2a. But what if we have a cubic equation instead? Do we still have a very nice formula for its vertex? And the answer for that is yes, because that formula looks very similar to the quadratic formula. So today, let's talk about that. But I will first have to clarify what I mean by the vertex. Here, let's have a look at the graph of a cubic function. The ones that we are going to focus today will look like this. Something like up, down, and up. Or maybe down, up, and down. Because these are the only two kinds of cubic graphs that will give us a vertex here and also the vertex here. But I shouldn't be calling them vertices because this is not the highest point because the graph keeps going up. And this is not the lowest point because you can see that is certainly lower than that. The correct terms I should be using is this is a local maximum because locally speaking, meaning if you just narrow it down to maybe like this region, this is the highest point. Similarly, this right here is called a local minimum. So what we are really trying to do is we are trying to find a formula for the local min and also the max of a cubic graph. But unfortunately, not all the cubic graphs have local min, local max. Because for example, if you look at the graph y is equal to x cubed, it looks like this. Go up, it becomes flagged, and then keep going up. This right here is flagged, but it's not local min, it's not local max. Or maybe if you look at y is equal to x cubed plus x, the graph looks like this. It goes up, and then continuously goes up, it doesn't even stop. It looks like that. So these are not the cases that we are trying to get because they have no local min or max. So later on, once we get the formula, we'll talk about what the conditions to really have a local min, local max for cubic and how to identify them. Now, we have to be honest with each other. I know you know, and you should know that I know too. We can just take the derivative of this and then set it equal to 0 and then solve for x and then we'll be done. But since everybody knows that, let's not do it. No calculus in this video to make this more interesting. So how can we do it with just algebra? Well, let me show you. Here, let's go back to the local maximum of this picture. Here, let me draw a horizontal line. So here we have a y value. I'm just going to call that y value k. Now, let's take a look at the graph. This right here goes up, hits this wall, right, kind of like a wall, and then it bounces back down like this. So what's going to happen is that if I set this part to equal k, then that equation will have a double root. So what do I mean by that? Here, this is actually what we did with the quadratic as well. If today I give you a quadratic equation with the graph that looks like this, y equals ax squared plus bx plus c. As we can see, here we have our vertex, and I can do a horizontal line. I can call that y value k. Now, to find the vertex of a parabola, we can complete the square, and this is a standard form of a quadratic equation. Once you complete the square, you can put that into a vertex form, and it's like this: a times x minus h squared plus k, where hk is a vertex. Now, have a look. If I set this equation to equal k, subtract k to both sides, then we have just this part is equal to 0. X minus h squared equal to 0, that means h is a double root. And that's exactly the x value of the vertex. And we have a formula for that. It's just negative b over 2a. So the double root is the key. And of course, right here, if you set this to equal maybe another k, So let's say this is k1, this is k2. This will also give you a double root. Right here, let me call this double root R1, and let me call this R2. But you have to set at two different the k values, right? But in fact, it's not that complicated. All we have to do is set this equal to k, and then force to have a double root. And that R expression will give you the x value for the local min or local max. Before we go to the next page, I have to tell you, we have to make sure that the R is just a double root. We cannot have a triple root. Because if you look at this, if you set x to the third power equal to 0, then 0 is a triple root, because technically you are saying x is equal to 0, x is equal to 0, x is equal to 0. When you have a triple root, you don't get a local min, you don't get a local max. So double root is the key. Now, let's make that happen. So we want to set our equation ax cubed plus bx squared plus cx plus d, set it equal to some k, and we have to make sure that it has a double root. And let's call it R. And later on you'll see k really doesn't matter, because k is just the y value for the local min, local max. R is the x value for the local min and local max. And this is what we really care. Now, subtract k to both sides, you get ax cubed plus bx squared plus cx plus d minus k being 0. If R is a double root for this equation, that means we should be able to factor this and get a factor of x minus r squared. Just like we had the x minus h squared from the quadratic earlier. But in this case, we have this times something else, and that's equal to 0. And then right here, to figure this out, we can just do synthetic division, because we can take this divided by x minus r, and then take that result divided by x minus r again. So let's make that happen. Synthetic division. Let's write down the coefficients. We have ax cubed, bx squared, cx, and then d minus k. And then dividing by x minus r, I just have to put the r on the outside. Bring down the a. Take this times that, we have ar. And for synthetic division, we add. So this is ar plus b. And then continue. We will have ar squared plus br, and then add them up. And then do it one more time. And we get ar squared plus br, so ar cubed plus br squared plus cr, and then just add them up. So ar cubed plus br squared plus cr plus d minus k. This is the remainder when we take this expression divided by x minus r. And it should be equal to 0. But of course, since r is a root, so if you plug in r into all the x's, that has to be 0, just like the expression that we have. In fact, this doesn't matter, because we will have to do this again. Now check this out. We have the r on the outside, and then put the a right here, and then multiply. Here we get ar. Add them up, we get 2ar plus b, and then do it again. Take this times that, we have 2ar squared plus br. Now, ladies and gentlemen, add them up, we have ar squared plus 2ar squared, that's 3ar squared. br plus br, that's 2br, and lastly we have the plus c. This right here is the remainder when we take this divided by x minus r squared. And in order for this to be a double root, we will have to make sure this remainder is set to be 0. And now I'm pretty sure many of you guys noticed what this is already, right? Yes, this is precisely the derivative of that. Plugging r. So let's just go ahead, set this equal to 0, and figure out what r should be. So we are looking at 3ar squared plus 2br plus c equal to 0 is a quadratic equation. We can just use the quadratic formula. R is equal to negative b, which is the 2b here, plus or minus square root 2b squared minus 4, and then this coefficient, which we have 3a, and then that constant term, which is just c, all over 2 times that coefficient. And now let's just simplify it. So that is negative 2b plus or minus square root. That is 4b squared, and then minus 12ac, all over, let me just keep it as 2 times 3a. You will see why. Here, 4 and 12, we can factor out 4. Instead of the square root, though, put it on the outside, it will just give us 2. So this is negative 2b plus or minus 2 square root. We took out the 4 already, so that's b squared. 12, factor out the 4, so we have 3, so minus 3ac, all over 2 times 3a. Both terms on the top have 2's. We cancel them out with the 1 on the bottom. So ladies and gentlemen, the formula that we have is negative b plus or minus square root of b squared minus 3ac, all over 3a. Look, this is just like the quadratic formula, isn't it? But here we have minus 3ac, and then here we have 3a. Now, let me just summarize all this for you guys. So that's the formula that we have. Now, to make sure that the results are real, we will have to make sure the inside of the square root is non-negative. So that means we have a condition, b squared minus 3ac, it has to be greater than or equal to 0. Secondly, we will also have to make sure this expression gives us two different R values, because one will be for the local min and the other one will be for the local max. And to make that happen, we just have to make sure this square root part is not equal to 0, because plus or minus 0 is the same thing. And then combine these two conditions together, we will just need b squared minus 3ac to be greater than 0 in order to make sure our cubic equation have a local min and also have a local max. But which one is which though? Well, that's the final thing. Finally, our equation with this condition, and then we have the R formula to tell which one will give you the local min and local max. It really depends on the A value. So let me give you guys a picture. Suppose A is greater than 0, then the graph is going to look like this. Starting from down low, and you go up, down, and up. Why? Because x cubed dominates the rest, and imagine if x is negative infinity. Raised that to the third power, it will be negative infinity times positive number. It will still be negative infinity, so that's why it starts right there. And this right here is going to be the local max, and then this right here will be the local min. In this case, the local max will have a smaller x value. Let me call that R1. And if you look at this formula here, the one that with the minus will give us the smaller x value, because this right here, it's never negative. So R1, let me just say that's equal to negative b minus square root of b squared minus 3ac all over 3a. Similarly though, R2, I will just call that negative b, the one with the plus. That will be the bigger x value for that. And in our case, R2 will give you the local minimum. And then of course, if you look at the other picture, when a is less than 0, this time the graph will go down, up, and then down. The smaller x value, R1, will give us the local minimum, and then the bigger x value here, R2, will give us the local maximum. That's it. This is the summary for how you can find the local min and local max of a cubic equation without doing calculus. And the formula just looks so nice, isn't it?